Okay, just a sec. You can see my screen. If you can, then just please type yes. Okay, welcome everybody. This is DGD 10th session. This will be about your chapter 34th from the book, and this will cover your wave motion, Snell's law, and ray optics. Okay. Okay, let's start from first question. The first question is, the reflecting surfaces of two intersecting flat mirrors are at an angle theta that is between 0 and 90 degrees as shown in figure. So this is the figure. For light ray that strikes the horizontal mirror, show that the emerging ray will intersect the incident ray at an angle beta. So we have to prove beta is 180 degrees minus 2 theta. So let's look at the diagram here. So when you have a light entering like that, then this angle, incidence angle, another incidence angle. Okay, I don't know if you can see it clearly. I'm talking about this angle. Okay, so what you can think is, and this angle is beta as well. This is beta. So 2i plus 2 alpha plus beta should be 180 degrees. And triangle OAB. In triangle OAB. Okay, beta is 180 degrees minus 2 iota plus alpha, where alpha is incident angle at point A. Okay, now call this point C, and this is theta. Triangle CAO, theta plus 90 degrees so this is actually like this. The drawing was, this is 90 degrees. Okay, so this is like that. This is 90 degrees as well. 90 minus alpha plus 90 minus iota to 180 degrees. Therefore, theta is equals to iota plus alpha. Therefore, equation 1, substituting in equation 1, beta is 180 degrees minus 2 theta, hence proved. Okay, so this diagram was little incorrect. I'll draw the right one just to clear any confusion if you have. Now you can see how there. This is 90 minus I. And this is 90 minus alpha. So did you get it? Please say something, then only I can go to the next question. So this is beta. You can type as well if you think so. Okay, I'll move on to the next question. I assume everything is correct. Okay, so the second question is light passes from air to flint glass at a non-zero angle of incidence. Let's draw them. So you have a boundary and then you have a beam. So that is air, that is flint. So theta I, theta r. Okay. Is it possible for the component of velocity perpendicular to the interface to remain constant? So if this is vi, vr, then this is the component we are talking about. So what the question is saying is that component perpendicular cos theta I should be equals to vr cos theta r. To prove therefore according to Snell's law n1 sine theta I equals to n2 sine theta r. N1 is 1. Refractive index of flint glass is 1.66, general glass. And so also VR can be written as C divided by 1.66 and VI as C divided by 1 multiplying equation 1 and 2. We get, when substituting these as well in equation 2, in equation 1, substituting in equation 1, we get sine theta I, cos theta I, sine theta r, cos theta r. Therefore, sine 2 theta I equals to sine 2 theta r, where sine 2 theta to sine theta cos theta. Okay. Okay. So theta I cannot be equal to theta r. So physically possible solution, as angle of incidence cannot be equal to angle of refraction. So physically possible solution according to above equation is 2 theta I is equals to 180 degree minus 2 theta r, or theta I is equals to 90 degrees minus theta r. Substituting in equation 2, in equation 2, we get sine theta I as 1.66 cos theta r. Therefore, sorry, this is cos theta I. Therefore, tan theta I 1.66, theta I 58.9 degrees. Therefore, answer to first part, yes, it is possible. So can the component of velocity parallel to the interface remain constant? So answer to your first part is yes, it can remain constant. constant if angle of incidence is theta I. Okay. B part. Can the component of velocity parallel to interface remain constant during refraction? Explain your answer. So now they're asking about instead of, so they're asking about this component. So component parallel. So can it remain constant? No, it cannot because because when speed of light decreases when it enters optically denser medium, optically denser medium, and it bends away from normal. Therefore, both the effects result in changing parallel component of light. Okay, so it's done. Do you like it? If if you get it, then I'll move on. Okay, I hope you got it.
Yeah, my chat pod just disappeared, but so far I've been getting it.
Okay, perfect. So let me see why it's disappeared. Just a sec. It's possible.
It's fine, I can just talk.
Just a sec. I'll just see if it's possible. If not, then I'll restore. Yeah, did it come back? I think so. It came back. Okay, perfect. So if at any point you didn't get it, I will repeat it again. So the question was whether is it possible to for the normal component of the light at the interface to remain constant, and the answer was yes. And for the parallel component, the answer was no. We proved why it was possible. Okay, perfect. If you got everything, I will move on to the next question. I'll read the question for you first. The index of refraction for violet light in silica flint glass is NV. That for red light is NR. What is the angular spread? So I'll give you NV is 1.66, NR is 1.62. Okay. Okay. So what is the angular spread of visible light passing through a prism of apex angle phi if the angle of incidence is theta. So we have to find dispersion or angular spread. We have to find delta theta. So let's call this theta v, theta r. So we have to find theta v, theta r minus theta v, the angular spread to find. Okay, so using Snell's law, let's call this incident angle as theta 1, sine theta 1, and 1 equals to n2 sine theta 2. I'll draw it for you so that it'll be more clear. Okay, okay. I'm not already good at drawing. Oh, there we go. So, and this should be with respect to the normal theta 1, theta 2, theta 3. Okay, now, and let's call them theta 4. Okay, n1 is 1, so it's from the air to the glass. Okay, so sine theta 1 by n2 equals to sine theta 2, right? So theta 2 violet is sine theta 1 by 1.66, and sine theta 2 sine theta I by 1.62. Okay, theta 2 red. Okay, so just give me a second. Let me correct this here. I think I missed in the question. I'm checking my question back again. I think I missed in the question the value of theta I. Just gonna recheck it. Just a second. Okay, if I get it or not. Yeah, so the question, the value is given as 50 degrees. So I missed it. So theta I is given as 50 degrees. Okay, so sine 50 divided by 1.66, that'll be 27.4. I calculated it before, and this will be 28.2. Okay, also this is 60 degrees. 90 minus theta 2, also 90 minus theta 2 plus 90 minus theta 3 plus 60 is equals to 180 degrees. So theta 2 plus theta 3 is equals to 60 degrees, or theta 3 is 60 degrees minus theta 2. Okay. Also using Snell's law at second boundary, let me, this is, I'll rename this as second boundary. Okay. So using Snell's law at second boundary, n3 sine theta 3 equals to n, n is 1, so I won't write it, sine theta 4. Okay, perfect. And theta 4, n3 is for violet, violet is 1.66 sine 60 degrees minus 27.4. Okay, I'm getting this from here and here. And theta for red has 1.62 sine 60 degrees minus 28.2. Okay, therefore we'll get just don't be confused there. So delta theta, angular spread, is equals to theta for violet subtracted by theta for red. It'll be around, so this will come out to be minus 58.56, 4.61. So this is the answer. Did you get it? I'll repeat it actually once. It is just using Snell's law at two boundaries. So what I did is I used Snell's law at boundary number 1. Then I tried to find the relation between theta 2 and theta 3 using the property of triangle. And then I applied the Snell's law at second boundary, and that's how I found the total angular spread or angular dispersion. Okay, I'll move on to the next question if it's okay. This one is a fun question. Let me just resize that. Okay. And the question says how many times will the incident beam in figure 34.33 be reflected by each of the parallel mirrors? So before escaping. So let me draw what's the condition here. We have two parallel mirrors. we have two parallel mirrors, and the distance is given as 1 meter. Okay, and we know, okay, so we have to find how many times will the incident beam be reflected. So we have to find how many times it will be reflected in 1 meter. Okay, before escaping. So how do you do it? Let's see, this is theta, then tan theta, where theta is given as 5 degrees. Tan theta is this side. Let's call it x. X divided by 1. Therefore, x is tan 5. That is 0. How much was it? 0.0875. 0.0875. Therefore, this distance will be 2x. Okay, so 2x is 0.175. So one reflection is 0.175, and total length of each mirror is 1 meter. The number of reflection is 1 by 0.175. That will be 5.72. That will be 5 reflections from right wall, or complete reflections, right wall, and 6 reflections from left wall, or left mirror. So did you get it? You can open your mic and ask me. It's just you and me. So
Okay, yeah. The original way I looked at it was just find x, like to be 0.0875, divide 1 meter by that, and then count how many times it bounces, but I
no,
understand.
but you have to see it is incident from here. Okay, so the full reflection will be when it reaches back the point. So that's how you'll find this will exit here, let's say, and then you will say, okay, so this is bouncing 3 times from the left and 2 times from the right. You get it?
Yeah.
Okay, so it will always like exit from the right side because it's incident from the right side. Because theta is very small.
Okay.
If the theta has been larger, then there will be a different story though. But the theta is very small. Okay, I hope it made sense. You can ask me then, or whatever. Let's go on to the diamond. Remove these. So did you try these questions before?
Some of them are from our homework, and then I've
Oh,
looked at the questions to see if I understood it at least.
okay. That's your assignment problems.
Yeah, like the one with the apex angle, the
This one?
dispersions. Yeah, that one's from our homework.
Wow, I didn't see that. Okay. So consider a, so let me go to the next question. So consider a light ray traveling between air and diamond cut in the shape. So it's given here. I'm horrible at drawing, so I'll just go with this one. So find the critical angle for the total internal reflection for light in the diamond incident on the interface between the diamond and the outside air. So for A part, we'll just use Snell's law using, it's a direct application. Okay, N1, that is N diamond sine. Let's call this theta I, N2 sine theta. So for total sine theta R, for total internal reflection, theta R is 90 degrees. Then theta C critical angle is N2 divided by ND, where N2 is 1, refractive index of air, and theta C is 1, sine theta C. Sine theta C is 1 by 2.419. Okay, and did I write the value? Okay, so I didn't write the value. Okay, this should be around 24.4 if I remember. I did calculate it, I didn't write it. This should be around 24.4, 24.4 approximately degrees. Okay, that's your critical angle. Sorry, sorry for that. That was shortcut. We should write that theta C is sine inverse 1 by 2.419. That should be equal to 24.4 degrees approximately, if I remember correctly. Okay, so let's move on to the B part of the question. Consider the light ray incident normally on the top surface of the diamond as shown. Show that the light traveling toward point P in the diamond is totally reflected. What if, suppose the diamond is immersed in water? So, B part, yes, it will be totally internally reflected because theta I is in the figure above is 35.0, which is greater than theta C, 24.4. Remove these one. Okay. Okay. So how did I get this as 35? This angle is 35. If I draw just a section of it, That is given as 35 degrees. I'll just prove it to you. How did I get it? And this is theta I. I'm claiming that this is also 35 degrees. Let me prove it to you. So if I draw that, this is also 35 degrees. Okay. This angle is 90 minus theta I, and this angle is 90 minus theta I plus 35 is equals to 90 degrees. So this cancels out. Theta I is equal to 35 degrees. I hope it makes sense. Just proving that theta I is 35 degrees. So theta I is greater than theta C. That means light will be totally internally reflected. So light will experience total internal reflection because incident angle is greater than the critical angle. Okay. What if immersed in water? Then theta C will be sine inverse 1.333 divided by 2.419. That should be around 33.2. Therefore, still theta I is greater than theta C. Light will experience total internal reflection. Okay. What is the critical angle of diamond water surface? We did that already. When the diamond is immersed, does the light ray emerging entering the top undergo total internal reflection? Yes, it will undergo total. So that's also the answer to C part and D part. Do you get it?
Yep, all clear.
Okay. Move on to the next part or the next question. Yeah, here. Okay. So the question is, a room contains air in which speed of sound is 343 meter per second. The walls of the room are made of concrete in which the speed of sound is around 4 times the speed of sound in air. Find the critical angle for total internal reflection of sound at the concrete air boundary. In which medium the sound be initially traveling if it is to undergo total internal reflection. And the third part is whether it's efficient mirror for sound. So let me draw the or okay. So here are your two mediums in which light, let's say sound waves are going like that. And it wants to know whether it will be totally internally reflected. So this is your concrete. What's this spell it? Concrete. This is your air. Speed is VI. The speed here is VC. Speed in concrete. So using total internal reflection or using Snell's law, using a Snell's law, Vi sine theta C is VC sine theta I. Okay, so VI by VC sine inverse is your theta I. Theta I is sine inverse 343 by 18 by 1850. Yes, this will come out to be 10.6 degrees. Okay, so this is initial speed of sound, that's speed of sound in air, this is speed of sound in concrete. I just applied the Snell's law, nothing that, and this is 10.6. So in which medium must the sound be initially traveling? So that's your critical angle. So sorry, that's 90 degrees, that is critical angle. Okay, so this changes to 90 degrees for total internal reflection. Okay, so B part, in which medium must the sound be initially traveling if it's to go on total internal reflection undergo? So that should be air. It should be incident from the air. Go to the C part. A bare concrete wall is a highly efficient mirror for sound. Give evidence for or against this statement. What do you think? Do you think it's a good efficient wall?
I'd say so.
You say so?
Because yeah, because the angle of incidence is so
Okay,
small
so
it
yeah,
lets
it
you like
is
talk right
because
at the concrete.
yeah, perfect. So also, if you can see the mountains, whenever you shout in the middle of the mountains or you say something loudly, it echoes, right? It echoes because it's reflecting back. Because your angle of incidence is very small, like for the critical angle is very small. So any sound waves greater than the critical angle will reflect back. That's why you hear the echo back. Get it? So yes,
Yeah.
as critical angle is very small. Any waves with larger incident will reflect back. Okay, so the last question for today. I hope the time is, yeah, we're not doing it. I'll read the question. If you want, you can turn off the mic because I'm hearing myself again. Perfect. So, an optical fiber has an index of refraction n and diameter d. It is surrounded by a vacuum light, and the light is sent to the fiber along the axis as shown. So, as shown, light is sent. Find the smallest outside radius or minimum permitted for a bend in the fiber if no light is to escape. Okay, so the case is like this. I'll draw it for you. Uh, okay, kind of like that. It has more curves though. Okay, let me draw it properly so no confusion there. Where so this is an arc. So this point is R. This is also R, and this is R minus D. This is D. Okay, so I draw it a little bad. Theta I. So before we proceed for the question, I'll make a statement. If you agree, we can move ahead. That the ray on the inner radii of fiber will have the smallest incident angle. Okay, so we have to
Yep.
find R min permitted for a bend in the fiber if no light is to escape. So we want the light to not escape, so we need to find the minimum incident angle, right? So according to Snell's law, we can see that because we are trying to find the critical angle, that's why we want to find the minimum, right?
Yep.
So theta c is sine inverse 1 by n, and so sine theta I or sine theta c or theta c, should I write now? Let's do sine theta c, or should be greater than sine theta c. Okay, minimum, your minimum incidence angle should be greater than sine theta c, your critical angle, then only your light will be totally internally reflected or experience DIR. Then sine theta I in this diagram, let's call it OAB in triangle OAB, sine theta I is R, sorry, R minus D by R. Okay, so using equation 1, using equation 1 and 2 and 2, R minus D by R, or let's call it R min, should be greater than 1 by n. Therefore, R minus D into n into R, and I can say nd equals to Rn minus R. No, there's a greater than sign. Right. So this will be opposite way. Okay. So R min should be greater than LD by N minus 1. So that's your answer for part A. Did you get it?
Makes sense.
Okay, thank you. I'll move on to part B. It's just approximation. So what result does part A predict as D approaches 0? Is the behavior reasonable? Explain. So as D tends to 0, then R min tends to 0. It is reasonable? Yes, because let me tell you why. Because as D tends to 0, then theta I will be very, very large, very, very greater, or very, very large. Let's call it not greater than 1. Theta is very, very large. That means if your radii is very, very small, then theta I large is possible. It's vice versa. Also, as n increases, what happens to your R min? So, see, as n increases, R decreases. So, if n decreases, d part, n decreases to 1, then R approaches infinity. Did you get it? How n increases, R decreases, and n decrease to 1, then R goes to infinity.
Yep.
Okay, it's just straightforward, just going from there to there. I'm just using this equation and answering all the parts. It's just approximating. So the last part is it will evaluate R minimum, assuming the fiber diameter is 100 microns and the index of refraction as 1.40. So you just need to put the values back. R minimum you can find using 1.40 into diameter is 100 microns. 0.40. That will be in microns. Okay. If you get it, then I'll conclude the today's session.
Yep.
Okay. So we covered in today's session, we covered several questions from your chapter 34 of the book, which covers your ray optics, wave optics, introduction to it, and Snell's law and total internal reflection. Okay, we covered several questions on that. And thank you very much for attending the session. I'll post it on Facebook, on YouTube.
Yep. Thank you.
And thank you very much.